Today we'll finally get into coding of some Linux kernel modules. Specifically, we'll code a module that runs when our custom device is connected, as well as disconnected from the machine. First, of course, we need a way to compile our module. There are some good news here because the kernel provides a build system we can use. To use it, we need to install a package called Linux headers in Ubuntu or kernel devel in Fedora. After that, we just create our own makefile, list our source code inside a variable that will be read by the build system, and link the build system itself. It will create a module with a KO extension which we can then load into running kernel using commands like insmod for insert module and rmmod for remove module. A little more detail, the build system expects the sources listed in a variable called obj-m, and the build system itself is then linked with the -c option. We'll look at an example of it in the coding section. The simplest module structure takes as little as creating 2 functions and calling 3 functions. In this scenario, we have to provide the callbacks that are to be called when the module is loaded and unloaded, as well as to register those callbacks in the system. Importantly, we have to define the license for our module. If it's licensed not under GPL, we won't be able to use other GPL licensed modules, which we will need. The simplest USB driver also takes 2 callbacks called when the device is connected or probed in the right terms, and disconnected. The driver also needs some information about the device it's running. We'll look at it in a moment. Before that, one little side note. While writing the code, we'll need some debug features. The kernel provides its own version of the printf function called printk. It takes similar arguments but prints to the kernel log. The same log we can access with the dmessage command. Alright, we're getting to the drivers. Here on the slide there is a bunch of penguins driving some kind of vehicle, because they are drivers. And they are penguins because, they are Linux drivers. Anyway, a driver in Linux is represented as a structure that contains information about some device and pointers to functions that define what to do during the interaction between the machine and device. There is a list of those structures stored somewhere in memory. So what we're going to do is to create such a structure and add it to a list of other drivers. The tricky part is the information about the device that the driver is able to run. It's another structure that contains a bunch of fields including class, subclass, protocol, vendor, and product ID. As we've seen before, a USB device also provides those fields in the device and interface descriptors. So the 2 sets of fields will be compared. If they match, the driver will be loaded for this device, otherwise it won't. This structure has a way to instruct Linux to compare only some of fields. For example, only the vendor and product ID, only class and subclass, and so on. Okay, that is enough theory at this stage. It must have been the most confusing theory part so far, but I hope it will be clear once we run an example. So let's get back to the code. I'm gonna need an empty folder for my driver. I will open the terminal window here. Now install the package containing the build system. There is a separate version of the package for every version of the kernel, so I have to find out which is mine. The uname -r shows the version I have. So I need to install 5.15.0-43 generic. Well, I already have this package, and when it's installed, a folder under lib modules named as the version of the kernel have to appear. This folder contains, among others, a makefile that will build modules. Next, I create my own makefile in my module folder, as well as a C source file. I'm gonna move these 2 files in the IDE and start by implementing the makefile. First, I'll have to mention my source file, then set the location of the actual makefile that's gonna build the module. Next goes the instruction for building. We simply call the makefile from the package we installed earlier and tell it to build the module in current directory. It will look in the obj-m variable to find out the sources. That is it for the makefile, and we can switch to the C file. We are going to include the header containing the module initialization functions and proceed by defining the functions themselves. All it's going to do is to print a line in the kernel log. Don't forget the new line character. The exit function is not going to be much different. Now we have to register these functions, as their names are arbitrary, but the module needs to know they have to be called when it's loaded and unloaded. Setting the license is also important, because Linux allows using GPL modules only by the modules that are distributed under GPL license. Now we are ready to build this. A bunch of new files had appeared. We're interested in the one with the KO extension. Now we can load the module using the insmod command. It seems to be loaded. Let's check the kernel log. And I see the message from my function, so it's working. Now let's unload the module and see the log again. The message from the exit function is there, so the module is working. Now let's register a new USB driver. I'm going to include the header containing USB related functions and call for a driver registration here by calling USB register. The function takes a structure containing information about the device, which I'm going to define now. Its type is USB driver. It's supposed to have a name, functions that are going to be called when the device is connected and disconnected. It's also going to have something called ID table that defines what device the driver is able to run. Importantly, we have to deregister the driver when it's unloaded. Now let's create the ID table, which is going to be an array of type USB device ID. We'll have to somehow list our device inside it. Luckily, we have a macro that could help us. This one, for example, defines a device by ID product and ID vendor. Now this driver will be loaded for the device that has ID vendor of 0483 and ID product of 1234, all in hex. This array have to include an empty structure at the end. This is how Linux will know that the array is over. Now I'll define the functions called when the device is connected and disconnected. Their definition is not intuitive, we're gonna get to it later. And all this function is gonna do is to print in the log. The disconnect function will be pretty similar. That seems good. I think we're ready to build this thing. Maybe it's not that good. It seems like I forgot to put some square brackets because ID table is an array. I also forgot a comma, build it again, and this time it looks better. Here I am trying to load this module with an incorrect command. A little patience, I'm gonna get it. Here we go. Now let's see the log. We have the probing message. I have my device attached. Let me disconnect it and refresh the log. And it says the device was disconnected, so our code does execute for our custom device. I reinsert the device again. The log shows some errors, probably because the device failed to respond to a device qualifier request. Anyway, our module is still executed for the device. Now let's take a look under the hood to find out how all these functions and structures are defined. I'm gonna open the kernel source code I've downloaded in the introduction part. Now open again my driver source. Let's take a look at this USB register function. I'm gonna search for it in the kernel code and have too much results, so I need some kind of filter. I know that USB-related API lives inside USB header we included in the code, and here we have it, actually pointing to another function. No problem, we can search this other function too. This time I remove the filter and only have one potential result inside a C file. Alright, we have a definition, and the only real argument here is the USB structure. Everything else will be filled automatically with that plain USB register function. So let's try and find this driver structure. Again, there is quite a few results, but we're interested in the definition. And we know that definition is gonna have a curly bracket, and there is only one result with a curly bracket in it. Okay, we have a structure that contains probe and disconnect functions, as well as some other callbacks like suspend and resume, which we don't use. One interesting field is actually this one, ID table. Let's try and find its definition. Insert it into the search prompt along with the curly bracket, and here we have it. It contains ID product, ID vendor, device class and subclass, interface class, protocol, all those fields we've been sending with the configuration request. Down here we also have a bunch of defines that list different match types, whether the device should be selected by vendor ID or product ID or class, protocol, etc. Now let's see what does this macro do, the USB device. I bet it is defined, so I'm adding this keyword into the search prompt. And here it is in the usb.h header. So all this macro do is it sets the IDs of vendor and product and sets the match type. Match device means both ID vendor and ID product match. Alright, we got somewhat working code that executes for our custom device, and this concludes this part. Next time we'll create a way for the user to communicate with the driver.